So today we are going to be talking about gyroscopes. So gyroscopes are devices used to measure the speed of angular rotation by sensing the magnitude of the Coriolis force acting on an object. MEMS gyroscopes differ from macroscopic gyroscopes in that they utilize orthogonal vibrational modes coupled by the Coriolis force. So we are going to talk briefly about the Coriolis force to kind of set things up here. All right, so let's say that we have a simple system wherein we have a disk. Imagine I can draw an ellipse that isn't terrible. All right, and this axis here is the axis of symmetry for our disk. And I'm going to label this point here on the outside edge point B. So if our disk is stationary and I throw a mass from the center of this disk towards point B, what's going to happen? After some amount of time, the mass will arrive at point B, and that amount of time depends on the velocity, right? So if I throw in this direction some mass m with a velocity like so, it will eventually arrive at point B. Okay, what if the disk spins with some angular velocity, capital omega? Okay, so same situation. I have a mass in the middle. I'm throwing it towards point B. But instead, the mass is going to arrive at some point A down here. And from an outside observer, the mass is going to take some curved path towards A, while A spins to move where position B was. This deflection of the path is the manifestation of the Coriolis force. Okay, so mathematically, our Coriolis force Fc is given by -2 times our mass times our angular velocity vector. And the direction of this angular velocity vector is the axis that rotation is occurring around, crossed into a velocity vector, which actually we've been using x prime in this class. So this is angular velocity, linear velocity, and mass over here. So it's important to understand we have a cross product here. So the directions of these things are critically important, right? So let's look at our reference frame that we have right now, right? And for those of you that are on Zoom, sorry, you can't use me or look at me using the right hand rule, but you can figure things out, right? So my index finger is representing the axis of rotation. So if I'm imagining my disk is parallel to the surface of this plate, this is my axis of rotation. I am directing my velocity out towards the edge of the disk. So that's where my middle finger is. And my thumb is going to point in the direction of the resultant, except that since there's a negative sign, it's actually going to go in the opposite direction, right? So if we look at this particular system, as the way that I've drawn it on the board here, the negative y direction explains why our path is deflected downwards towards that outside edge, right? So that is our Coriolis force that is manifesting here. Now, since the direction of velocity and like the linear velocity and the axis of rotation are typically orthogonal in a MEMS system, we can throw away that cross product term because that's just going to be sine of 90 degrees, which is 1. And so in most cases, this is going to be negative 2 m omega x dot, where we have to pay attention to our directions to figure out what direction that force is acting on. Okay, so let's briefly work a mathematical example here, right? So let's say that we have a micro resonator. Of mass m is equal to 1 times 10 to the minus 9 kilograms, 1 microgram. But because we're going to be measuring a force here, I wanted to be able to do simple calculations to find newtons. Is vibrating at a frequency of f naught is equal to 10 kilohertz. With a vibrational amplitude of x naught is equal to 1 micron along the x-axis. If the resonator is on a rotating platform, which spins at an angular velocity of capital omega is equal to 2 pi radians per second. So 1 revolution every second. With a rotational axis in the Z direction. What is the Coriolis force acting on the mass? So as Sam inadvertently discovered earlier when we were talking, we are going to look at this thing in the frequency domain. Okay. Because I don't like to have to do integrals and derivatives. I like to do algebra. Okay. So in the frequency domain, the resonator displacement can be written as x. It's going to be a vector. X naught e to the j omega naught t in the x direction, right? So in the frequency domain, this exponential here looks like sinusoidal oscillation, which is exactly why we use it to represent steady state sinusoidal systems. So we have some sinusoidal oscillation that has a maximum amplitude of x naught, and it is oscillating at a frequency of omega naught. So plugging in numbers here, we'd have 1 e to the j, 2 pi times 10 kilohertz is going to look like 2 pi times 10 to the 4 multiplied by t, microns of displacement in the x direction. Yes.
Can't really read the middle term. Displacement can be written as, I can't quite read.
This part right here.
No, in the description. Resonator displacement?
Yeah, resonator displacement.
Okay, that's a oh, okay. Yeah. That looks like, I'm sorry, it looks like I equals 50 something.
I will change my penmanship. I'm sorry about that. Resonator. Yeah, when you read it, I was like, I don't understand what you are. Okay. Does that look more like resonator?
Yeah.
Okay. Okay, my apologies for my terrible penmanship. All right, so let's start here. Are we all okay with this representing our displacement? Anybody have a problem or anything, right? Just to be clear here, the real part of this thing would be 1 cosine 2 pi times 10 to the 4t microns in the x direction. So that's what the time domain signal that we're representing with complex numbers, because I don't like doing calculus on sinusoids. So anyway, so if we want to take our Coriolis force depends on the velocity, right? So to find our velocity, we're simply going to take the derivative of this thing, right? So that's going to be nothing more than j omega times x, because in the frequency domain, taking the derivative is the same as multiplying by a factor of j omega. And so we're going to have j omega x naught e to the j omega naught t, which is going to look like j times 0.062 8, I'll leave it there. E to the J 2 pi times 10 to the 4 T meters per second. Also in the equation. So this J right here represents a 90-degree phase shift, right? So for the electrical engineering students, they probably all have a pretty good idea of what this means, but this is a mechanical system, right? So effectively what this J represents is a 90-degree phase shift between the velocity and the displacement, meaning that when the displacement is 0, the velocity will be at its maximum. And when the velocity is 0, the displacement will be at its maximum, right? So effectively, as this thing is oscillating, when it reaches the end point of its oscillation and has to turn around, the velocity has to be 0. So maximum displacement means 0 velocity. Similarly, when it's going through its oscillation, when it reaches that middle point, its displacement is 0, but it is traveling at the fastest speed possible. So that is how we're going to interpret our J in this case. All right. Coriolis force. FC is equal to -2 m omega crossed into x dot, which is just going to look like -2 m omega lowercase omega x naught. I'm going to throw a J out here in the front because there needs to be one there when I do that derivative. E to the J omega naught T. And putting numbers into this thing, it comes out to be -J 0.790 E to the J 2 pi times 10 to the 4 T nanonewtons, and the direction of the force will be in the y direction. So the Coriolis force that is experienced by a MEMS microresonator is incredibly small. Okay. So that means that we have to be very careful with our design, because the magnitude of this force is often comparable to the magnitude of noise forces and things like that from our system. So just random vibration things here. Another thing that we need to point out here is that the magnitude of the Coriolis force, and we can see it by looking at this portion right here, right? So that's our magnitude of our Coriolis force. Not only is it proportional to our speed of angular rotation, capital omega, that our system is undergoing, but it is also proportional to the displacement that we are experiencing, x naught, right? So in order to maximize our Coriolis force that we can see, making our measurement either, we need to maximize the displacement that our device undergoes. Another thing that hopefully is maybe not super obvious right now, but since our Coriolis force depends on a velocity, that's why we have to have a resonator or something moving to begin with in order to measure a Coriolis force. If we don't have some form of vibration to start with, we cannot observe the Coriolis force in effect. Okay. So let's look at a simplified version of the two-mode gyroscope. We want it to be as large as possible because that's what we're trying to measure, right? So effectively, what's going to happen? So let's let me draw this picture actually, and it'll make a little bit more sense of what we're trying to do here, okay? So this is a simplified view of a vibrating two-mode gyroscope. Okay. So this is fundamentally how 99.99% of MEMS gyroscopes work. So on the left-hand side here, we are going to have an anchor. We have a frame here in the middle. And on the right-hand side, we have another anchor, right? And so we are going to have, thank you, that's killing my head, springs that are coupling our frame to these anchor points. Well, in the center, we're going to have our proof mass that is coupled to our frame with springs. And so if we imagine that this axis is our drive mode, so this is where we're going to experience drive vibrations. If we have, let me put down a coordinate system here. So let's call this direction the X direction, this direction the Y direction, and let's see, into the board the Z direction. If we experience rotation about the Z axis, our Coriolis force is going to induce vibration in the Y axis, right? So this is the direction of our sense vibrations. So if we are rotating about this axis, right? So we're spinning around and we're going back and forth, and then we start to spin, we're going to see that we get vibrations in the Y direction due to the Coriolis force acting on our system, okay? So what we effectively have here is two harmonic oscillators that are vibrating in orthogonal directions whenever there is a Coriolis force acting on the system, right? So for a simple harmonic oscillator, we know that our force is our mass times the second derivative of our mass displacement with respect to time, plus our damping coefficient times the first derivative of displacement with respect to time, plus our spring force, okay? So we are going to use the Laplace transform with specific initial conditions to make the math easier and figure out how this thing works in the frequency domain, okay? So just as an aside over here, we are going to say that our initial displacement at t is equal to 0 is 0, and our velocity at t is equal to 0 is also 0. So we're starting from a rest position. In the S domain, our force will be equal to M times S squared X plus gamma times SX plus KX. Right, or our second derivative is just multiplying by S squared. Our first derivative is multiplying by S and so forth, with the initial conditions of 0 for the displacement and the velocity. Okay. We could write this as ms squared plus gamma s plus k times x, which allows us to write a transfer function for our system. H of s will be the ratio of the displacement to the force, which is simply 1 over that second order polynomial, ms squared plus gamma s plus k. We are going to mess with things slightly here, and you'll see why in a moment. And we are going to effectively multiply the numerator and the denominator here by a factor of 1 over m. So that would give us 1 over m in the numerator. And then m times 1 over m obviously just looks like s squared. Gamma over m times s. And then k over m goes here, right? Well, this is another aside thing here, a substitution we're about to make. We know that the mechanical resonant frequency of our system is the square root of k over m. And we know that the mechanical quality factor of our system is omega naught m over gamma. So if we substitute in those relationships, we get a transfer function of 1 over m times 1 over s squared plus omega naught over q times s plus omega naught squared. Everybody okay? Anything too wild or crazy here? Q is the quality factor. It's what we talked about when we were dealing with damping in our last couple of class meetings. Okay. So if our system is undergoing steady state sinusoidal oscillation, because we're driving it to do so, right? S is going to be equal to just j omega, right? So we're not going to have any exponential decay term in our oscillations. We are just going to have pure sinusoidal vibrations. So H of j omega, which allows us to work in the frequency domain, is going to be 1 over m times 1 over j omega squared plus j omega times omega naught over q plus omega naught squared, which is 1 over m times 1 over omega naught squared minus omega squared plus j omega times omega naught over q. And what I'm going to do now is I'm going to break this thing up into its real and imaginary components. And we'll see why I'm doing this in a minute, okay? So to break this thing up into its real and imaginary components, I'm going to multiply by the complex conjugate of the denominator over the complex conjugate of the denominator. So that's just going to be a factor of omega naught squared minus omega squared minus j omega times omega naught q over this exact same thing. So this is going to give me 1 over m times. So I'm going to have a real term that is just going to be omega naught squared minus omega squared in the numerator here. And I'm going to look at my denominator here. So I'm going to have omega naught squared minus omega squared squared plus, so when I have positive j times a negative j, that looks like positive 1 omega times omega naught over q quantity squared. Now I'm going to have my imaginary part, so this is going to look like minus j omega times omega naught over q divided by that same denominator, omega naught squared minus omega squared quantity squared plus omega times omega naught over q squared. I promise you guys there is a method to the madness here, okay? So we've split this transfer function up into constituent parts. So this is generic for any simple harmonic oscillator. We have two simple harmonic oscillators, one for our drive and one for our sense. So we're going to use this same transfer function for both, but everything is going to have a subscript of D when we're looking at the drive side, and everything is going to have a subscript of S when we're looking at the sense side, okay? So using this transfer function, okay, so this is, so we don't have to do convolution in the time domain, which for those of you that have dealt with signals and systems, you don't want to do. We can say that our drive mode displacement as a function of frequency will be our drive mode transfer function as a function of frequency times the drive force as a function of frequency. And our sense mode displacement as a function of frequency will be our sense mode transfer function times our Coriolis force, because that's what's causing the vibrations there. We're going to add another term to this that we're going to talk about on Wednesday. We are also going to have epsilon sub q times xd as a function of frequency. Okay, so this term here represents what's called quadrature error. And this quadrature error arises due to manufacturing limitations. So effectively, we are expecting our vibrational mode, our drive mode, and our sense mode to be perfectly orthogonal to each other. But what if the reactive ion etching or whatever that we use to fabricate our springs makes one of our springs slightly more stiff than the other ones? We are going to induce a small degree of vibration in that sense mode by exciting our drive mode. And so the quadrature error EQ term or epsilon Q term represents what fraction of the energy goes into that spurious mode. Okay. So we're taking into account that we may have errors. So with this information in our pocket, okay, let's talk about the different vibrations that we're going to see. So earlier, I had mentioned that the Coriolis force that is experienced by our mass here is proportional to the vibrational amplitude, right? So the vibrational amplitude is our drive mode vibration here. If we want to make this vibrational amplitude as large as it can possibly be, what frequency should we excite the drive mode at? The resonant frequency. Absolutely right. So in MEMS gyroscopes, the drive mode is usually excited at the mechanical resonant frequency of the drive system to maximize the displacement and therefore the experienced Coriolis force while minimizing the power input and energy consumption of the device, right? So effectively, if we excite this system at omega naught D, we can put in the smallest amount of energy to get the largest displacement out of it. So at omega is equal to omega naught D, our drive mode transfer function reduces to, now let's just come up here and look at this, right? So we're looking at this bottom relationship here. So when omega is equal to omega naught, what happens to the real part of our transfer function? 0, right? So we're only dealing with the imaginary part. Absolutely, okay? This portion of it also goes away. So that portion of the denominator, right? So we have omega times omega naught, which is just going to be omega naught squared over Q divided by omega naught squared over Q quantity squared. So this is just going to look like H sub D at omega is equal to omega naught D is going to look like negative J 1 over the mass of the drive portion, because it can have two different masses, times QD over omega naught D squared. Well, what's mass times resonant frequency squared? Spring constant. Absolutely right. So this is just negative J QD over KD. And from this, our displacement XD at omega is equal to omega naught D is just our transfer function times our force, negative J QD over KD times our driving force, where we can see that our displacement is 90 degrees behind the application of the force. So we have a lag effectively. Okay. Excuse me. So for our sense mode vibrations, we are going to assume our quadrature error term is 0 to start with. So assuming epsilon q is equal to 0. The sense mode displacement is given by xs as a function of omega will be equal to hs of omega times our Coriolis force. And so this is going to be a really ugly complex number. We'll talk about specific cases that are commonly utilized here in a moment. So 1 over ms times omega naught s squared minus omega squared divided by omega naught s squared minus omega squared squared plus omega times omega naught over q quantity squared minus j omega times omega naught over q, omega naught s over qs. Forgetting my s's in some places, I apologize. Over that same denominator. Square that, close that. Now I'm multiplying by my Coriolis force. So I'm going to write this out like this, and then I'm going to make a change to it. So negative 2 m d, because it's the mass of the drive mode that is experiencing the Coriolis force, times capital omega times the drive mode velocity. Now the drive mode velocity is just j omega times xd, our drive mode displacement, right? So I'm going to throw a j here, and I'm going to throw an omega xd here. And now I'm going to multiply these things together. And so what this is going to give me, so there's going to be a common negative factor here, right? So I say that because obviously when I multiply this first part by this negative number over on the right-hand side of my Coriolis force, that's going to give me a negative thing. Then I have negative j times negative j, which is going to look like positive j squared, which is -1, right? So I have a common negative 1 over m sub s. And then this is going to look like twice md xd capital omega lowercase omega squared omega naught s over qs divided by omega naught s squared minus omega squared squared plus omega times omega naught s over qs squared plus j, and it's plus because I factored that negative sign out of the whole thing. Another ugly fraction here. Twice md xd capital omega lowercase omega omega naught s squared minus omega squared over that same denominator. So that is what my sense mode displacement looks like. And this is going to simplify depending on the frequency that we use. So there's two common ways to excite, or two common frequencies that are used, okay? So we could have a matched mode system, right? Where omega naught S and omega naught D are the same things, right? So in this case, so let me, I guess I should specify here. So the omega that we're looking at here, this lowercase omega without any subscript, that is the excitation frequency of the drive mode, okay? So if the drive mode, if we're exciting the drive mode at omega naught D, which we know we're doing to maximize displacement, and omega naught S is equal to omega naught D, we're going to see that a lot of these terms go away. For example, in this match mode system, the imaginary part of our displacement automatically goes to 0, right? Because we have a factor of omega naught S, which is equal to omega naught D minus omega naught D squared. All of that goes away, and we're left only with so our sense mode displacement reduces to XS of omega. So I'm saying again, I don't want to do this too much because we're going to come back to this equation. That term is going to go away. That whole term goes away. And so we wind up having -2 MD over MS. Then we're going to have XD capital omega. So on the bottom there, we have omega naught S squared over QS, quantity squared. Okay. Don't write this down, Stephen, because you're just gonna have to erase it in a moment. I'm just giving you a fair warning. So what I've written to this point is good to go, but we're working our way through the algebra here, right? So we're going to have omega naught S to the 4th power over QS to the 2nd power when we are operating at omega is equal to omega naught S, which is equal to omega naught D. And then up here in the numerator, we have omega naught S squared times omega naught S, which looks like omega naught S to the 3rd power over a single QS, right? So this QS cancels out one of the powers here. This omega naught to the 3rd cancels out this guy here. And that whole thing reduces to QS over omega naught S. So our displacement here is proportional to the ratio of the masses. Our displacement, our drive mode displacement, our rotational frequency. It's also linearly proportional to the quality factor of the sense mode, right? Which means in order to get a large displacement to measure, right? We'll talk about that in a moment. We need to have a high quality factor. Well, if we have a high quality factor, we inherently have a low measurement bandwidth, because the two things are inversely related, right? So what I mean by that is for a system with a high quality factor, and I'm going to draw this simple graph and then I'm going to erase it. So I'm just giving you fair warning right now. So for a system with a low quality factor, the response looks something like this. For a system with a high quality factor, we have that point of ringing. And so our bandwidth is very, very small. So this is our bandwidth as opposed to this being our bandwidth, right? So a high quality factor inherently means we have a low measurement bandwidth, which can be okay, but can also be problematic. Another problem with using matched modes is that it's expensive because we have to make sure that the resonant frequency of our sense mode and the resonant frequency of our drive mode are literally identical, right? So that means that we either have to probably physically trim our springs, meaning that we have to go back through and literally laser etch to make sure that our spring constants and the ratio of spring constant to mass works out perfectly for both the drive and sense mode, or we have to include extra circuitry to electronically trim or match our vibrational modes, right? So this is absolutely a possibility, but it's typically more expensive to do it. The second method that is commonly used is called separated mode systems. So for separated mode systems, the resonant frequency of the sense mode is much higher than the resonant frequency of the drive mode. And in a system like this, the sense mode displacement will reduce to. So now let's look at this thing here again. I can erase these red lines, right? So we're looking at a system where omega naught S is much greater than the omega in this case, right? So I would argue that our first term here is effectively going to go to 0 because omega squared times omega naught S is going to be much smaller than omega naught S squared here, right? This term of our denominator of this portion is also going to look insignificant to omega naught S squared, okay? So what we're going to wind up having, and this term should also go away. What we're going to wind up seeing is a sense mode displacement of approximately negative J twice MD over MS times XD capital omega lowercase omega over omega naught S squared. Okay. So to be clear here, the omega naught S squared term in the numerator gets canceled by the omega naught S squared term in the denominator. So that's where that omega naught S squared term comes in. And so we just have the numerator 2MD XD omega, capital omega times lowercase omega divided by MS times omega naught S squared. Okay. So this is our displacement in a separated mode system. once again, to get a large displacement, we need to have a large sense mode displacement. We need to have a large drive mode displacement. The same factor of twice omega d times, twice md over ms shows up. We can actually simplify things here a little bit because we have in our denominator ms times omega naught s squared, which looks like the spring constant of our sense mode. So this will be negative j twice md xd capital omega lowercase omega divided by k sub s. And it makes it obvious that if we want to see a large sense mode displacement, we need both a large drive mode displacement and soft springs in our sense mode. All right. So now I'm going to draw pictures. Yeah, we have enough time for this. Actually, let's talk about things here real quick before I finish writing that thought down. So integral to good operation of a gyroscope, we have to be able to get large drive mode displacements. So which of the actuation schemes that we've covered do you think would be useful for this? So let's talk about stuff. Piezoelectric displacement. What did that get us? Really large forces, really small displacements, right? Thermal displacement, typically pretty small displacements, and it takes a lot of time to generate those displacements because it takes time to heat up our material. And if we want to have a sinusoidally oscillating displacement, we would have to heat and cool and heat and cool and heat and cool our material, which is going to be pretty hard to do at the micro scale, right? What other displacements did we talk about?
Electrostatic.
Electrostatic, absolutely, and magnetic. Both of those are used. Electrostatic is by far the more common way to drive a gyroscope, okay? So we are going to focus on capacitive or electrostatically driven gyroscopes here. So I'm going to draw two pictures, commonly used designs. And we're not going to analyze them just yet, and you'll see why in just a moment. Okay. So let's start with this first system. So this thing right here is representing my proof mass. And then I'm going to use, so actually let's talk a little bit further. So we've decided on capacitive actuation. What type of capacitive actuation? We want to induce sinusoidal movement.
Is there any particular reason why we could use it home drive and lateral displacement?
So that is exactly what we're going to use, because comb drives give us an easily controllable lateral displacement. We're going to put a comb drive on both sides so that we can cause it to move back and forth. We just have to make sure that our actuation is timed correctly so that our forces are pulling in the right direction. So you're nailing it, Steve. So I'm going to put a comb drive over here on the right. And a comb drive over here on the left. And I'm going to have a similar thing on the next one that we're going to draw. I'm going to draw the drive mode things over here. And this bit is the stationary bit. Similar thing over here on the left-hand side. All right. So this set of comb drives is our drive electrode, and it allows movement from left to right. So this is going to be common to both of the designs that we're looking at here. So let's do this one first. Now I'm going to put some springs up here. This big thick beam is so that it doesn't deform. I'm going to have a similar deal on the bottom. So these are my drive mode beams. They're what's establishing my spring constant and therefore my resonant frequency of my drive mode. And then down the middle here, I'm going to put an anchor point. This is going to be my sense mode beam, so I'm just going to allow it to move in whatever direction it needs to move in the sense mode, which should be fairly obvious to figure out because beams in extension don't move. What we are saying here is our axis of rotation is the down direction, right? So my same way. So as we have on the screen, my axis of rotation is in the down direction, like we see on the screen, and my movement is left to right. Then I'm going to see that my plate is going to move into and out of the page. Okay, so that is the direction of motion that I'm going to see. So now I have to figure out, well, how am I going to measure that direction of motion? A parallel plate capacitor, right? Where I'm going to do this in a different color. If we put a plate underneath here, and our plate needs to be big enough that effectively our capacitance does not change as our structure moves from left to right. Any Coriolis force experienced by this system will cause our central plate to move up or down, causing the sense capacitance formed by that plate and that electrode on the substrate to change, giving us a voltage signal that is proportional to our rate of angular rotation. So from a side view kind of thing here, let me draw this. This is our sense electrode. Which we have here. Over here, we have our anchor. Here in the middle, This is our plate. And then there are fingers that are sticking off of the plate, like so. And then there are fingers that are interdigitated from the mass section, and we should see that our sense mode displacement is in the up and down direction, changing the distancing between those two plates, which gives us a changing electrical signal. Okay. So that's one way to do it. This is a pitch or y-axis rotation sensor. Okay. Now, let's look at a similar system. Actually, another thing here. No. So that's one way that we can do it. Now let's look at a similar design, but for a different rotational axis. So once again, we have our mass here in the center, and we're going to have left to right drive mode displacement. Using a capacitive comb drive. All right. So what if we wanted to measure rotation in the plane of the mass? We measured rotation out of plane a moment ago, right? So if our axis of rotation was directed out of the mass and our movement is in that same direction, like so. So our mass is out of the plane. Excuse me, our rotational direction is out of the page. Our velocity is along that horizontal axis. We are going to see that the Coriolis force is going to induce movement along the vertical direction. So how are we going to measure changes in that vertical direction? With another comb drive. So we could have a system, something like this. So this is going to be a big chunk of business here. So these springs are allowing left to right movement. So these are our drive springs. These springs that I'm drawing here, we're going to have an identical system on the bottom. These are our sense springs or beams. And then attached up here, we'll have another comb drive. And this comb drive allows us to measure the vertical displacement using a capacitive system. And I'm just drawing a matching set here on the bottom. All right, so oh, we only have a minute left of class. All right, so what I want to talk about at the very beginning of class on Wednesday then is how do we generate sinusoidally varying forces, right? because our drive force in this system needs to sinusoidally oscillate. When we talked about capacitive or electrostatic actuation, and we were dealing with comb drives, we assumed that we were using DC voltages to pull it one direction or the other. Now we need to cause that electrostatic force to vary so that we get sinusoidal oscillation. So we're going to talk about that briefly. Probably work an example problem, tying all of this together, and then talk about quadrature error and how to fix it. And then we're done. Sound like a plan? Yes, sir.
For the exam, slide.
I need to get the review guide up, so I'm going to go work on that literally here immediately. Hopefully I'll have it up before 2 p.m., which is when I have my next class. I'm also going to try to knock out at least 2 to 3 homework assignments per day to get them uploaded until we are quote unquote caught up, so that your first ones you'll have effectively 2 weeks to do, and then it'll get shorter and shorter as we get to the end of the week. But by the end of the week, they should all be up. Does that satisfy your questions?
Yeah.
Okay, great. Yes, I meant to do it over the weekend, and then my wife gave me too long of a list of crap to do, so I apologize. And for our coordinate system here, just to be clear, this is the X direction, this is the Y direction, and we are experiencing rotation in the Z direction.
Dr. Holden, somebody just asked about.
That's okay.
Dr. Hartman, somebody just asked about presentations at the end of the quarter.
Yeah, so I said when we had class on Friday that we weren't going to do them because I never gave you guys an assignment sheet, and I thought it would be unfair to make you come up with something, so I'm not going to. Instead, we are changing the grading to be 1/3 homeworks, 1/3 exam 1, 1/3 exam 2. Which we again discussed, I thought, not at length, but for about 5 to 10 minutes at the beginning of our class on last Friday, if my memory serves me correctly. So.
Okay, so which one is sensitive? Vertical, but.
So in the Y direction, right? So,
Okay, that's what I thought.
yeah, so not out of,
Yeah, you said vertical.
yeah, so no, that's my fault for vertical on the page, but not vertical out of the, yeah. So our rotation is occurring in the plane of the mass.
Yeah.
So omega's vector direction is out of the page. Our movement is in the X direction. Our drive mode movement is in the X direction. And so our thumb points in the direction of our sense mode displacement. And I'll just put it on here.
Yeah, that's why I just needed to have some error.
Yep, absolutely. Because that's the wacky thing about gyroscopes is you would think, oh, well, if I push it in this direction, all of our experience with a linear frame of reference would be it'll move in this direction. But for a gyroscope, if we push it, it moves 90 degrees shifted from the way that we would expect, which is
So